Welcome to another episode of A10X, brought to you by 10 Leaves.
Glad to be here for this one.
So, if you just take a second and look around, you look at your phone, your computer, or, the battery powering all your devices.
Right, the stuff we use every single day.
Exactly. I mean, the battery inside that phone took decades of grueling bench work, endless funding, and just agonizing trial and error to invent.
Oh, absolutely. Years of dead ends.
But the next generation of that battery, and artificial intelligence might architect it in, 45 seconds.
Which is just mind-blowing to even think about.
It really is. And today, we're pulling apart a fascinating excerpt from a piece called Synthesizing the Future, AI in Material Science.
Really profound piece of writing.
Yeah, and our mission for this deep dive is to explore this massive paradigm shift in how the physical world around you is actually built.
Right, because we hear so much hype about AI writing text or, making images.
Making funny pictures of cats.
Yeah, exactly. But AI stepping out of the digital realm to literally design the physical materials of the future, that is arguably its most world-changing application.
Totally. So let's unpack this. To understand how AI is changing material science, we first have to look at the core mechanism the source highlights, which is prediction.
Prediction is the key word here, yeah.
Because AI can predict material property before they are physically created. And normally, science feels very, hands-on.
Very messy, mixing things in beakers.
Right. Trial and error. So if the traditional method is like blindly mixing ingredients in a kitchen and just hoping the cake tastes good.
Which is a slow process.
Right. Then AI is like having a master chef who can mathematically taste the recipe, know its exact texture, and perfect it before ever turning on the oven.
That is a perfect analogy because the fundamental bottleneck in the history of material science has always been wet lab synthesis.
The physical creation part.
Exactly. You hypothesize a molecular structure, you spend months, sometimes years, just trying to synthesize it, and then you finally test its property.
And it might not even work.
Often it doesn't. So what this source material outlines is skipping that bottleneck entirely.
So we're just predicting it digitally. But wait, haven't we had computer simulations for a while? Like, scientists have used software to model molecules for years, right?
We have, yeah. But to understand the leap, you have to look at how we used to calculate those properties. Historically, it was quantum mechanical modeling.
Okay, sounds complicated.
It is, specifically something called density functional theory, or DFT.
EFT, right.
Right, and DFT calculates the actual quantum behavior of electrons to figure out how a molecule is going to behave.
Which I'm guessing is pretty accurate.
Incredibly accurate, but it is computationally agonizing.
Agonizing how? Like, it takes a few hours.
Try weeks.
Yeah.
Running a DFT simulation on a complex molecular structure could take a supercomputer days or even weeks to finish.
Wow.
It's basically the equivalent of trying to predict how a car will crumple in a crash by individually calculating the physical trajectory of every single atom in the bumper.
Okay, yeah, that sounds like a nightmare, especially if you want to test, 100,000 different bumper designs.
Which is exactly what you need to do to find a breakthrough material.
Right.
So that's the friction point. But the AI models, the source, discusses these graph neural networks. They don't calculate the physics from scratch every single time.
Oh, they don't?
No. They are trained on massive data sets of already completed DFT calculations.
I see.
So on known real-world material properties. So the AI learns the underlying patterns of chemistry.
So it's not solving the math equation, it's just recognizing the pattern.
Exactly. So when you feed it a new molecular structure, it simply predicts the outcome. It bypasses the quantum bottleneck entirely.
Wow, turning a simulation that used to take weeks into a prediction that takes, what, seconds?
Fractions of a second, actually.
That's nuts. So going back to the chef analogy, it's a master chef who has mathematically mapped the flavor profiles of millions of past recipes.
Yeah.
And this chef knows exactly how molecule A will interact with molecule B to create, say, a specific density without ever needing the oven.
And that map you just mentioned, it's literal.
Wait, really? A literal map?
Yeah, in machine learning, this is called mapping the latent space.
Latent space.
Right. The AI creates this vast, multidimensional geometric map of chemistry.
Okay, wrap my head around that. Multidimensional.
Imagine a map where molecular structures with similar properties, say really high thermal conductivity, are grouped together.
Clustered in one corner of the map.
Exactly. So by navigating this latent space, the AI can mathematically traverse the gap between a known conductive material and a completely novel, undiscovered structure.
So it finds something new that shares those properties, but maybe, I don't know, weighs half as much.
Exactly. It's exploring the uncharted territory on the map.
Okay, that leads us right into the next major point from our sources. Because, speed is completely useless if you're sprinting in the wrong direction.
Right. You have to aim it at the right problems.
And the text specifically highlights where we are pointing this predictive engine. It mentions three foundational pillars: batteries, electronics,
Yep.
and sustainable products.
The big three.
Yeah. Now, batteries and electronics, that makes immediate sense to me. We all want our phones to run longer and our computers to process faster.
Absolutely.
But sustainable products, that is an incredibly broad umbrella. And frankly, this is where I find myself pushing back a bit.
Oh, let's hear the skepticism. Where does the process break down for you?
Well, isn't the AI fundamentally limited by the data it was trained on?
Yes, it is.
Right, so they learned chemistry from our last century of industrialization, which, let's face it, heavily relied on toxic, non-degradable, carbon-heavy materials.
It's a dirty data set, yeah.
Exactly. How does it spontaneously invent a green alternative? It feels like asking a 19th century oil baron to design a solar panel.
But that's a great way to put it.
Like, are we just throwing darts at a digital board hoping to find something green?
Yeah.
How does it innovate out of a toxic data set?
That is a brilliant question. And it really cuts to the heart of how these algorithms synthesize new ideas.
Okay, lay it on me.
The AI isn't just memorizing specific toxic plastics and spitting out variations of them.
It's not.
No, it's learning the fundamental relationships between atomic bonds and material properties.
Okay.
It learns why a certain toxic polymer is incredibly strong, but it also learns why a completely different, naturally occurring compound biodegrades easily in soil.
Oh, I get it. So it's looking at the underlying rules, not just the final product.
Precisely. It is learning the rule book of physics.
Wow.
So the magic happens when you ask the algorithm to explore the untouched areas of that latent space. We discussed the spaces between known materials.
So you tell it to combine them.
Basically, you ask it to find a novel structure that has the high tensile strength of the toxic plastic, but also has the specific chemical cleavage sites of the biodegradable compound.
That's wild. So it designed something that has never existed in nature.
Never existed, but the laws of physics dictate it should work perfectly.
It's solving a massive paradox when you explain it like that.
How so?
Well, true sustainability usually demands conflicting traits. Right? Like a biodegradable phone screen sounds great for the landfill, but if it shatters the second I tap it or melts if I leave it in my car on a hot day, it's entirely useless.
Exactly. Consumers won't buy it.
Right. So you are essentially asking the AI to find a material that is tough as nails when I need it, but turns to harmless dust the second it hits salt water.
Yep. And in material science, this is known as a multi-objective optimization problem.
Multi-objective optimization.
Right. Finding a material with one specific trait is relatively easy.
Sure.
But finding one that balances 3 or 4 deeply conflicting constraints, durability, high heat tolerance, cheap manufacturing, and environmental benignity.
That sounds mathematically staggering.
It is. Traditional bench work might take 20 years just to inch toward an acceptable compromise.
20 years.
Meanwhile, AI evaluates millions of permutations in an afternoon. It finds non-obvious folding techniques or alternative bonding mechanisms that a human chemist would likely never even consider.
Which completely explains why the source inextricably links sustainability with batteries and electronics.
They're completely connected.
Yeah, because we cannot scale the future of computing without advanced energy storage. And we can't scale battery production without revolutionizing its ecological footprint.
Exactly. We're currently reliant on mining rare earth metals, which, has a devastating environmental cost.
Right, so we are basically playing three-dimensional chess with chemistry, trying to invent a battery that holds a massive charge, doesn't catch fire, and can be synthesized from abundant, non-toxic elements.
And the solid-state battery is a perfect example of this intersecting crisis.
Oh, I've heard of those. How do they fit into this?
Well, for decades, researchers have been trying to replace the liquid electrolytes in lithium-ion batteries.
Because the liquid is the part that's flammable, right?
Yes, it's flammable, and it degrades over time. So we want to replace it with a solid, crystalline material.
Makes sense.
But finding a solid that conducts ions as quickly as a liquid while remaining chemically stable at room temperature, that is a monumental challenge.
You can imagine.
But right now, AI models are generating hundreds of thousands of candidate crystal structures for solid-state electrolytes. predicting their stability and conductivity before a single crystal is even grown in a lab.
That really contextualizes the scale of what we are discussing.
It's massive.
Yeah, it means we are moving entirely away from the search and find model of human history.
The search and find model.
Right. Because for thousands of years, humanity basically just dug stuff out of the earth, looked at it, and tried to figure out what it might be good for.
We found iron, we figured out how to forge it.
Exactly. We found petroleum, we figured out how to burn it. But this algorithmic approach flips that entire timeline backward.
It's a completely made-to-order model.
Yes. It's like walking into a tailor and ordering a custom suit. But instead of specifying the wool and the cut, we are giving measurements to the periodic table.
I love that. And the technical term for that made-to-order model is inverse design.
Inverse design.
Yes. The source material leans heavily into this when it talks about the future being designed by algorithms. It is a complete inversion of the traditional scientific method.
Okay, so what does this all mean for you, the listener? Let's dig into that term, inverse design. How does that contrast with the way we built the modern world?
Well, think about the silicon age.
All right.
We identified silicon, discovered its semiconductor properties, and then basically spent the next 70 years constraining our entire computing architecture to the limitations of that specific element.
Oh, wow. I never thought about it like that.
Yeah, we built massive cooling systems just to deal with silicon's heat generation. We forced our technology to conform to the material.
Because that's what we had.
Exactly. That is forward design. You start with the material and you build outward based on what it allows.
So we were essentially chained to whatever properties the Earth randomly provided us.
Exactly that. And inverse design shatters those chains.
How so?
You do not start with a material. You start with a real-world problem.
Okay.
You define the exact, rigorous parameters of what you need. You tell the algorithm, I need a coating for a wind turbine blade that repels ice at -40 degrees Celsius.
Right.
Withstands continuous gale force impacts without microfracturing and contains 0 forever chemicals like PFAS.
So you are basically handing the AI an impossible wish list.
You hand it the wish list, and the algorithm works backward.
It just figures it out.
It navigates that immense latent space of chemistry we talked about, analyzes atomic interactions, and synthesizes a blueprint for a completely novel molecular structure that satisfies those exact constraints.
It's not just browsing a catalog of known elements to find the closest match.
No, it is fundamentally architecting a new reality from the ground up to solve a bespoke problem.
You know, it is so similar to writing code, but the output isn't a software application.
Right.
The output is physical matter. You are essentially programming physical properties into existence.
Yes.
You type a prompt, and the result is a new kind of glass or a new superconductor. And that brings us full circle to the sheer magnitude of the text we've been examining.
Because the implications stretch into every industry imaginable.
Yeah, aviation, healthcare, renewable energy infrastructure.
All of it. The bottleneck of human innovation has always been the physical limitations of the materials available to us.
Right.
By removing the wet lab speed limit and shifting to this algorithmic inverse design, we are unlocking a rate of progress that the physical sciences have never experienced.
Incredible. So let's do a quick recap for you listening to kind of tie all these threads together.
Good idea.
We started by exploring the mechanics of prediction, how graph neural networks allow us to bypass those excruciatingly slow quantum calculations of the past.
The DFT bottleneck.
Right, mapping out the latent space of chemistry to predict material properties in milliseconds. Then, we saw how this computational velocity is specifically targeting the multi-objective optimization problems of our era.
Right, balancing massive power demands for batteries and electronics with the non-negotiable need for true sustainability.
Exactly. And finally, we arrived at the concept of inverse design. The shift from digging up materials and figuring out what they do to defining our most demanding real-world problems and letting algorithms architect custom molecular solutions.
It's a huge shift.
It is. The source leaves us with an incredibly powerful premise. The materials that will define tomorrow's technology are likely being simulated inside an AI model today.
They are. But, absorbing all of this actually raises a rather haunting question about the immediate future.
Oh, a haunting question.
Yeah, about manufacturing. We have established that these AI algorithms can beautifully navigate mathematical space to design a revolutionary material, right?
Right. They can perfectly balance conductivity, durability, and sustainability in a purely digital simulation.
Exactly. But what happens when the algorithm designs a material whose molecular structure is so wildly complex, so completely unprecedented, that our current physical factories simply lack the tools to synthesize it?
Oh, wow. That is a phenomenal catch.
It's a real possibility.
It would be like a supercomputer handing us the perfect, flawless blueprint for an interstellar spaceship, but we look around and realize all we have is a hammer and some nails.
Right. The design is perfect, but the execution is physically impossible for us right now.
So we could find ourselves in a bizarre historical gap.
An era where the AI tells us the exact molecular sequence required to cure our energy storage crisis or eliminate plastic pollution.
But bringing that digital molecule into the physical world requires a manufacturing process we haven't even conceived of yet.
Exactly. The ultimate paradox of this technology might be that AI's imagination and computational brilliance could vastly outpace our physical reality.
Man, now that is a thought to chew on. Next time you look at that phone on your desk or tap that glass screen, just think about what invisible, mathematically perfect materials are being dreamt up inside a server right now.
Waiting for us to catch up.
Exactly. They're just sitting there in the latent space waiting for human manufacturing to catch up so they can finally become the devices of tomorrow.
It's an exciting time.
It really is. This was AI 10X brought to you by 10 Leaves. Thanks for joining us on this deep dive.